Welcome dear students to the another video lecture on solid states. Today we will discuss a new topic regarding defects in solids. Okay, so we have seen solid arrangements, okay, like this, that there is a solid three-dimensional solid arrangement, okay, and there are interstitial sites, okay, like corners, face and center of the crystal, and atoms are occupied by those interstitial sites. So sometimes due to some reason some impurities occur in the crystal of the solid. There are generally two types of defects. One is called point defect, okay, eta ki hai point defect hai. What is point defect? Point defect occurs when there is ion or positive or negative ion or one of the constituents atom is missing from one of the interstitial point, okay. So this is called point defect. And another is called line defect, when in entire row if the same thing is missing, then it's called line defect or crystal defect, okay. So in our +2 syllabus, in our class 12 syllabus, we will discuss only point defect, okay. So further, point defect are of two types: stoichiometric and non-stoichiometric defect. Stoichiometric defect, okay. So stoichiometric defects are those defects which does not change the stoichiometry of the solid. It does not change the stoichiometry, okay, does not change the stoichiometry of the molecule, okay. Now we will see different type of stoichiometric defects, okay. The first one is, I think it's vacancy defect. Vacancy defect. So vacancy defect, just as the name suggests, vacancy defect, the vacancy defect occurs due to vacancy of any particular atom. Suppose there is an arrangement like ion, suppose atom A, atom B, okay. So A, B, A, B, this is the arrangement, okay. It should be arranged like this, and suppose one of the A is missing, okay, one of the A is missing from its original position, okay. And to maintain the electrical neutrality, okay, I will show you how electrical neutrality is balanced in such cases, okay. The ions will move, but the stoichiometry will not change. But see, if one A is missing, then its density will what? Decrease, okay, because its mass is decreasing. One atom is missing here, okay. So due to vacancy defect, okay, when vacancy defect occurs, so vacancy defect occurs when an atom or ion is absent at its original site, okay, and it decreases the density of solid. Then we have another, it's called interstitial. Okay, what is interstitial defect? Suppose these are the locations where atoms can come. Suppose it has A, B, so center is also a lattice point, okay. So suppose an extra A appears here, Okay, we can balance it also. Electrical neutrality will be balanced somehow. Okay, so if an extra A appears here, okay, this is called interstitial defect. Okay, so it will do what? Since an extra atom A is appearing, so it will increase the density of the crystal or substance. Okay, so in vacancy defect the density decreases, and in interstitial defect the density increases. Okay, now the vacancy and interstitial defects are generally shown by non-ionic compounds. Okay, generally molecular solids show these type of defects. Now what kind of defects is shown by ionic compound? Okay, so there are two type of defect. One is called Frankl, okay, Frankl defect. Frankl defect, okay, and in Frankl defect what happens? Suppose this is sodium, this is chlorine, sodium, chlorine, sodium, chlorine. It should be sodium, but suppose sodium is not present here, it's absent. Okay, so chlorine, then sodium, chlorine, sodium, chlorine. So one sodium is not here, and this sodium for any reason suppose appears here. Okay, so what is happening? The total number of sodium positive ion is the same. Okay, how many sodiums should be there? 1 2 3 4 5 6. There should be 6 sodium in this crystal. Okay, but one sodium is absent at the interstitial site where it is supposed to be there. It was supposed to be there, but it's not there. Okay, it shifted to another location. Okay, so since the amount is not changing, in Frankl defect density of the solid remains unchanged. Okay, because see, the number of overall number of ions is not changing. Okay, 6 sodium, there are 6 sodium and there are 6 chlorine only. What is happening? One sodium atom has been shifted from its original position. Generally, what you should note down about this defect? So see, there is a vacancy defect. Since the ion is not at its original position, and interstitial also, that means Frankl defect is an example of both Frankl and interstitial defect. Why? Because the absence of sodium from this location. जब किसी एक पॉइंट से कोई एटॉम या आयन बाहर निकल जाता है तो उसे हम क्या कहते हैं? वैकेंसी. यहाँ वैकेंसी हो गया है ना, खाली जगह बन गया, सो ये वैकेंसी डिफेक्ट है. अच्छा, जहाँ नहीं होना चाहिए वहाँ अगर एक एटॉम आ जाता है तो उसे क्या कहते हैं हम? इंटरस्टिशियल डिफेक्ट. इंटरस्टिशियल डिफेक्ट. तो फ्रैंकल में क्या हो रहा है? व्हाट इज हैपनिंग इन द फ्रैंकल डिफेक्ट? बोथ थिंग्स आर हैपनिंग साइमल्टेनियसली. वैकेंसी भी क्रिएट हो रहा है, इंटरस्टिशियल पॉइंट पे वही सोडियम फिर रीलोकेट भी हो जा रहा है, यानी दोनों चीज साथ साथ हो रहा है. यानी कि फ्रैंकल डिफेक्ट जो है वो एक एग्जांपल है. इट्स एन एग्जांपल ऑफ बोथ वैकेंसी एंड इंटरस्टिशियल डिफेक्ट. ओके, दिस इज समटाइम्स आल्सो नोन एज delocalization. Why? Because it has been delocalized from here to here, so it is also referred to as delocalization defect. Okay, second thing is, it is generally shown by smaller ions, generally cation. Okay, if cation is small, so those cations which are smaller in size generally show this defect. Okay, and examples are given, okay, like zinc, okay, zinc 2 positive ion or silver positive ion, okay, they in their ionic solids show these kind of defects. Okay, now, okay, let it stay like this. Now we will see Schottky defect. Okay, let me write it down. So it's Schottky defect. So what kind of defect is a Schottky defect? Okay, so what will happen? It will happen in a different way. Okay, what we have seen here, in case of Frankl, we have seen that sodium was relocated to this position, and so number of sodium and number of chlorine were equal. Okay, and since number of sodium and number of chlorine were equal, so the neutrality was maintained. Okay, neutrality was maintained. That means it was neither positive nor negative. Okay, why? Because number of cation and number of anions were equal. Okay, but now what will happen in Schottky defect? What happens? Suppose a sodium is absent. Okay, a sodium is absent. Now since one sodium is absent, that means number of chlorine has increased, because there are 5 sodiums and 6 chloride ions. So what will happen? One chlorine ion will also disappear. Okay, that means equal number of cation and anion will disappear. Okay, if one cation is missing, then one anion will also be missing. Okay, and in that way the electrical neutrality will be balanced. Okay, okay, so this is basically a vacancy defect. As you can see, the elements are the ions are not delocalized. Okay, they are not localized to another position, but only missing. Okay, the spaces are vacant. Okay, यहाँ पे सिर्फ खाली हो रहा है, कोई किसी दूसरे लोकेशन पे जा नहीं रहा है. So Schottky defect is a type of vacancy defect. Okay, now since it's a vacancy defect and we lost one sodium and one chlorine. Okay, so it's very obvious that density will decrease, isn't it? The density will decrease because we have less sodium and chlorine. Okay, now in general for sodium chloride, okay, if we take 1 centimeter cube, okay, 1 centimeter cube is what? If I take a crystal whose length, breadth and height is 1 centimeter, okay, if we take 1 centimeter cube of a sodium chloride crystal, then it will contain around 10 to the power 6, that means 1 million vacancies in it. Okay, 1 million vacancies in it. Okay, now this is shown by sodium chloride, potassium chloride, cesium chloride and so on. And there is one thing you should keep in mind: AgBr, silver bromide. Silver bromide can show both Frankl as well as Schottky defect. Okay, so since silver bromide can show both the defects, it's a very important example to remember. Okay, because what will happen? These type of questions are generally asked in the examination, that give an example which can show, give an example of a ionic solid which can show both Frankl and Schottky defect. Okay, and these small concepts should also be remembered, as which of the they can ask you that which of the following will show a decrease in density of the solid, Schottky defect or Frankl defect. Then the answer should be Schottky defect. Okay, because we have seen in Frankl defect density is unchanged. Okay, now we will see another defect, and it's called impurity defect. Okay, impurity defect. Okay, so what is impurity defect? Suppose we have sodium, chlorine, sodium, chlorine, sodium, so this kind of arrangement is there, suppose. Okay, now suppose instead of a sodium I take a strontium ion. Okay, strontium ion, but see that strontium is 2 positive. Okay, if it is sodium positive, then see we have 6 sodium, that means we have plus 6, and we have 6 chlorine, that means minus 6. Okay, now if I introduce a strontium here, what will happen? 4, 3. The positive charge is becoming 7 and negative charge is still minus 6. So it will change the neutrality. Okay, so in order to balance the neutrality, what will happen? Once sodium will vacate its position. Okay, so what will happen? It will again come down to plus 6. Okay, so this is called impurity defect. Okay, what is happening here? In this case, to maintain the electrical neutrality, okay, once sodium, okay, is absent from its interstitial site or position, okay, and that means strontium replaces 2 sodium. See, strontium is replacing this sodium which was originally here, and it is replacing this sodium also. Okay, since it's 2 positive, so it is replacing 2 sodium atoms from the crystal. Okay, so this is called impurity defect. Okay, because this is impurity. Okay, so this is impurity defect. Now we will discuss some non-stoichiometric defects. Non-stoichiometric defects. Okay, so obviously it will change the stoichiometry. If stoichiometry was not changing the stoichiometry, then non-stoichiometric will obviously change the stoichiometry. Okay, okay, in non-stoichiometry, one is metal excess defect. Now metal excess defect, I must not rub this because I have to use it all the time. Suppose this is the crystal arrangement of sodium chloride. Now what happens when sodium chloride solid is heated under sodium vapor? Okay, sodium vapor. If we heat solid sodium chloride in a sodium vapor environment, what will happen? Some chloride ions will appear on the surface. Okay, and on the surface what is there? There is sodium vapors. So sodium vapor is Na. Okay, and suppose this chlorine comes to the surface. Okay, ये क्लोरीन अगर सरफेस पे आ जाता है तो भी वो इसके साथ कंबाइन तो नहीं हो सकता. It cannot combine with sodium because chlorine negative can only combine with sodium positive. Okay, chlorine negative can combine with sodium positive. So what will happen? This sodium, from sodium vapor, it will lose an electron and become Na positive. It will lose an electron, and what will happen? This electron will enter here. Okay, this electron will enter here. So what this electron will do? This electron will balance the neutrality. See, because now positive and negative are equal. Okay, but one chlorine from the crystal fled away with this sodium from the sodium vapor. So one chloride ion is less. Okay, this crystal has a vacancy of one chloride. Okay, so what has happened? See, we have 6 sodium ions, but we have only 5 chlorine ions. That means metal is the concentration of metal is more than the non-metal or anionic part. That's why it is called metal excess defect. Okay, so this is your metal excess defect. Okay. Oh, and one more thing you have to remember about this. See, it has a free electron. Okay, it has a free electron, unpaired electron. So because of this unpaired electron, normal sodium chloride is what? Colorless. But as soon as you heat sodium chloride under sodium vapor, what will happen? In one of the chloride ions place, एक chloride ion की जगह क्या आ जाएगा? एक इलेक्ट्रॉन आ जाएगा, unpaired electron, and this electron can absorb energy from visible spectrum and can radiate it back. Okay, so it will show a color. Okay, light yellow. Okay, the color of this solid, it is also sodium chloride only. So this sodium chloride, after heating with sodium vapor, it will be light yellow in color. Okay, similarly if you do it with lithium chloride, the color will be the colors are given here. Lithium chloride will be pink, potassium chloride will be, you know, lilac color or violet, something purple or violet type. Okay, sodium chloride. Okay, so these are also, you know, something like which can come in examination. Now one is metal excess defect due to presence of extra cation at interstellar sites. Okay, defect due to extra cation. So what happens if we heat zinc oxide? If we heat zinc oxide, what will happen? We will get zinc 2 positive and half O2 plus 2 electrons. Okay, yeah. Okay, so zinc 2 positive, half oxygen and 2 electron. That means, see, as soon as we heat the zinc oxide crystal, an extra zinc 2 positive, that means zinc cation has appeared. But this zinc, we don't have to worry about the neutrality, because to balance this zinc 2 positive, we have 2 electrons over here. Okay, we have 2 electrons. Okay, so the electron neutrality is balanced. But what will happen? The formula will now change. The formula, this x represents any number. Okay, the formula will change. The formula will no longer be Zn-O. It's Zn1 plus xO. Okay, so the formula of the molecule has changed due to heating. Okay, so this is called metal excess defect due to presence of extra cation, this extra cation. Okay. Now next defect is metal deficiency. Okay, metal deficiency. Now what is metal deficiency? Take an example of FeO. Okay, ferrous oxide. Now we know we have written the formula of ferrous oxide theoretically. Theoretically it should be Fe2 positive and oxygen negative, but practically we see that when we get FeO, it ranges from 0.93O to Fe 0.96O. Okay, that means the iron is not completely 1, but it is fractionally less than 1. Here it is 0.7 less than 1, here it is 0.4 less than 1. Okay, so it can range from 0.93 to 0.96. That means we can see that the percentage of metallic part is lower than expected. And why such thing happens? Because of we sometimes Fe2 positive, some positions of Fe2 positive is taken by Fe3 positive. Okay, Fe3 positive. So balancing changes. Okay, the balancing or electrical neutrality thing changes, and as a result we get a lesser amount of iron in the solid. Okay, so this is all about the deficiency in the solids. Deficiency. Okay, go through these topics from your NCERT textbook. Okay, and drop your queries. Okay, your questions if you have any. Now we will talk about conductivity of the solids. Conductivity. Okay, conductivity. So I am sure that you know that there are three types. One is conductor, non-conductor or insulator, and semiconductors. They are very good conductors of electricity. They do not conduct electricity, and they can conduct electricity to some extent. Okay, now we will discuss about the reasons and something. We will not discuss conductor and insulator in detail. We know that the conductivity, okay, or resistance provided by a conductor is very high. Okay, so is very low. I'm sorry. So that's why conductors are, they can conduct electricity. Insulators, they have high electrical resistance, so they do not allow electrons to carry the electrical charge. Semiconductors fall in between insulators and conductors. Okay, fall in between the insulator and conductor. So we will see mainly the bonding part, how bonding things changes. Okay, so we will continue this in the next topic. We will discuss conductivity and magnetic behavior. Okay, thank you.